So scientists went about actually colliding different subatomic particles together and then detecting what came out of it. They thought that the world was going to get a lot simpler. Uh, and they thought that they would be able to understand a little bit more the bits that actually made up matter. But really, initially it got quite a bit more confusing. You'll see here a whole bunch of different particles. Now this is just a fraction of the new particles that were discovered. There's 300 particles that were discovered. Uh, and they were all brand new and exotic, and scientists were getting pretty confused. Now, one thing you'll notice from this chart, one way that we can actually identify these particles is their energy to speed of light ratio, where that comes from Einstein's equation. So you'll see these units often when talking about really small things, because it doesn't make much sense to talk about the mass of these things in terms of kilograms, because it's a very small amount of kilograms. But if we rearrange this equation, we get this relationship for mass. So the electron, for example, has a mass of that in terms of mega electron volts per c squared. I can get kilograms from that if I want. I take my mass of the electron in terms of that energy. That's 10 to the 6 electron volts. I can determine how much that is in joules, so 1.6 times 10 to the negative 19. And then I can divide by c squared, 3.00 times 10 to the 8. That's meters per second, and that's squared. And I can get 9.1 times 10 to the negative 31 kilograms. So I can convert this into kilograms if I want. This just comes from this equation. So E equals mc squared. It's another way to express very small masses. And that's kind of how scientists went about organizing these different particles. And so they took these 300 fundamental particles, and based off of things like spin and their mass and charge, they divided them into a couple of different groups, into leptons, where there were only 6, and there's 6 antiparticles that were discovered, and then hadrons, which are a little bit bigger. They interact using the strong nuclear force. They discovered hundreds of those. And then they divided them further based on spin into mesons and baryons. But that's kind of how they went about organizing that particle zoo. And so they got to this point where they were very confused. Now, out of that, though, they started to look at these hadrons. They looked at the leptons and like, well, these leptons, there's only 6 of them, and they're pretty small, so there's probably nothing smaller than those. Those are probably fundamental particles. And then they looked at the hadrons and like, well, there's lots of these. Maybe these are made up of smaller particles. And that is where this standard model came about, where we can actually determine and we can produce a lot of these hadrons using just 6 quarks. So these quarks are actually the bits that make up protons and neutrons. You'll notice an electron here is a lepton. A lepton. These leptons are still kind of the smallest bits. And then there's the antiparticles for all of these as well. So for an example, there's an electron. It has a charge of -1. A positron would have the same mass energy ratio, but it would just have a positive charge. An antiparticle, an anti-up quark, would just have the opposite charge, so it would be a positive 2/3 charge, or negative 2/3 charge, and an anti-down quark would have a positive 1/3 charge. Now scientists looked at these and they're like, well, we can use these to actually explain what's going on. Typically the ones that we need to be more familiar with are these first generation fermions, where we have our up quark, our down quark, our electron neutrino, which we observed in beta decay, and our electron. And from this we can actually determine a lot. In this standard model as well, you'll notice these bosons, which are these virtual particles, they're the actual force carriers which allow these things to interact. There's the photon, which is the carrier of the electromagnetic force, the gluon, which is the carrier of the strong force, and then the Z and W boson, which is the carrier of the weak force and responsible for radioactive decay. Now, getting back to these quarks, we can actually use these quarks to determine what makes up a proton. A proton has a +1 charge. And we can use just 3 quarks to show what a proton's made up of. We can use an up quark, which has a +2/3 charge. We can use another up quark, which has a +2/3 charge. And we can use one down quark, which has a -1/3 charge. And these are the 3 quarks that make up a proton. 2 up quarks and a down quark. We can also explain a neutron based on quarks. So a neutron has a neutral charge. So I can have one up quark with a +2/3 charge. But to have a neutral charge, I need 2 downs. So this down's -1/3, and this down is -1/3. And so these are the quarks that actually make up a neutron. Now, if I had an antiproton, antiparticles, typically we just draw them with a line over top. I would have two anti-ups and an anti-down quark. And all that would happen is I would change the sign on the charge. So I'd have -2/3, -2/3, and +2/3. That would give me an antiproton. So we can have antiparticles as well. There are these fundamental particles, up, down, and an electron, and then we can have their antiparticles also. Their antiparticles just has the opposite charge. Same magnitude, same charge to mass ratio, just an opposite charge. Now, scientists actually in Stanford, using one of those very early linear accelerators, were able to find evidence that supported this quark theory. They found that the electrons, when shot at protons, actually deflected differently around the proton. They deflected more on this side where I have these up quarks, which a +2/3 charge, and they actually slightly deflected away on this side with a down quark with a -1/3 charge. So that really supported this quark theory. And so that's the standard model. And again, typically we need to be familiar with this first generation, and then their antiparticles, which is just the opposite charge. We put a line over top to show an antiparticle, and an anti-electron is usually shown just like this, but we could also show it that way, and we call that a positron.